Okay, so I guess I can begin on the next set of slides. Let's go back to the start. Okay, make it full screen. Okay, so this sort of after the introduction, now the introduction to the introduction. So this is really talking about sort of basic R features, yeah? So that we sort of good to get familiar with, so we have a good understanding of the basics. So when we load up R, we sort of always sort of see this very similar thing each time, which is kind of print out telling us which version of R we're using. So this might change, but then these other statements are that there's no warranty with R, and that just sort of cite the packages that you're going to use, and then some of the basic demo functions and the help we talked about, the help start as well for the full manual. And Q to quit, although we don't really need to use that in our studio. So the main thing to notice from the sort of when R is loaded is the very last sort of character, right? This cursor here. So right at the bottom we see this this is what we call the prompt. So when you see this symbol in R, it means that R is sort of not doing anything and that it's waiting for an input, right? So we call it the prompt. So whenever we see the prompt, it means we can enter a command into R. So for example, we could type 3 minus 1, and it's going to give us the result. So when we type in anything into R, what it's doing is sort of using its the computer's active memory. So R knows what 1 is, and it knows what 3 is, and it also knows what a minus is. So it's able to sort of do the calculation. And in doing it, what it's doing is sort of creating a little object, right, a little bit of memory that then sort of works out the computation given these other bits of memory, right, the 3 and the minus and the 1, and then prints the contents, the results to the screen. So R sort of lets you know that it's finished, that it's printing an output using these sort of square brackets, and these square brackets tells us that the results are calculated and sort of how many results there are. So in this case, at the top here, right, there's only one result, right? It's just a one number, but it might be that you get a whole column, like a whole vector of numbers, and then you might have lots of square brackets giving you the sort of number of results. Okay, and this last point is that we can sort of scroll through previous commands that we've done by at the console pressing up or down. Let me just show you that in action. If I go back to the console right at the bottom, right, so it's waiting for an input, and I'm just going to press the up button, and then it's going to go back through the past commands that I've sent to R each time, so we can sort of see them there. So it's another way just to quickly go back and test and modify your R code. Okay, so sometimes when you're sort of writing R code, you might either write it at the prompt or even from a script. You might get something appear where you get you were expecting the square brackets, so you're expecting a result, right? But you're not getting it, and instead you get this plus. So this plus is actually R telling you that it's gone into a new line and it's continuing to wait for some other inputs. So here we just press 3 minus. We typed in 3 and then minus, and then we pressed enter like we want to find the result. And it's not giving us a result, right? It's giving us a plus sign, telling us not that we want to add something, but that we like a mathematical add, but that we want to add some more code, because at the moment it doesn't know what to do with 3 minus. It needs something else to complete the code to be able to do the calculation. So so occasionally I recommend, if you're getting this and you're not sure what's going on, you're always seeing a plus, you're not seeing these square brackets, then you can sort of get out of pressing any giving additional R commands by pressing escape or Control C, and this will allow you to get back to like a fresh reset of the R commands. So let's just show an example again. So I just press enter a few times. So let's do 3 plus 6 times by nothing. So I'm going to press enter like I want the result, and every time it's not telling me the result, so I can either complete it, right? I can do times by 8 and it gives me the result, or let's go back, or I can press escape and then I can go back and start again, not get a result, and sort of start afresh. Okay, so this is just what I mentioned, it was demonstrating, right? So we can either give a number to complete the result, or we can press escape. So this is less typical that it's working with a very simple calculation like this, but it does happen once in a while that you might have opened a parentheses, a bracket, and you forgot to close the parentheses, especially when you have lots of layers of parentheses. Then you might get to the case that you are seeing this plus because it wants you to close a bracket that you opened. Well, another sort of typical case is that you might have used a quotation mark. If you're giving a label to a category, for example, you might have opened the quotation mark to give a label, but forgot to close the quotation mark. So then you can either close it on the end of the next line or press escape. So remember, if you're in this kind of hole, the syntactic hole, right? Syntax, like the code that it wants something extra, but you can't quite figure out whether you need to close a bracket or close a quotation, then you can always press escape to sort of reset. Okay, so now we just go through some basic, very basic operators. So R can work like a very basic calculator, right? So we can use the plus and minus for addition and subtraction, the star and the divide for multiplication and division, and this kind of, how we would say, like a hat for raising to the power, right? So 10 to the 2 is 100, right? So we could do 10 hat 2 to get the same thing in R. So R sort of observes standard rules for operator procedure. So for that, I mean, if we use brackets, it's going to work out what's going on inside the brackets before doing the division, right? So 7 divided by brackets 1 plus 3 is not the same as 7 divided by 1 plus 3. So yeah, this can help you making sure that everything's evaluated in the operator, in the procedure, that the order that you like. So R also allows you to type in strings of characters, right? So this is what we mean by a label. Usually, we talk about them as strings, as text strings or character strings. So to do so, we use the quotation marks. So we can use double quotation marks or single quotation marks. And once we open one, we need to close one, right? So if we type something without quotation marks, then it sort of knows that it's looking for, you're essentially telling R to look for a function or an object, like a data frame. And if that doesn't exist, then you're going to get this error message. Okay. So here you see I wasn't getting an error message because I was putting it in quotation marks. So I was sort of telling R I'm creating a label. Whereas here there's no quotation marks, so it's telling R look for the object or look for the function called guy in this case. So we'll go a little bit into more depth on objects a little bit later. Just remember, if you're using text, if you're using strings, we need to use quotations. Okay. So with R code, you tend to see this quite a lot, the comment operator. And this tells R to ignore everything printed after the comment operator. So this is really useful when you want to add some notes to your R code. So you could write in here, like here I'm adding one, doing some addition, right? And but when it gets to really more complicated analysis, then it's always good to add in some comment operators and sort of tell yourself what's going on. So I often find, even when I look at code that I wrote maybe a few weeks ago, I can forget what I was doing. So I always try to get into sort of a good practice of writing little notes to myself or to others if I'm working on collaborative projects, to sort of say what sort of each section of code is doing. Okay, so with the comment operator, right, it can break code. So here everything works, right? We did 3 minus 1, but it's not adding the 20 because it's sort of, as I said, it ignores everything after the comment operator. If we put it in the wrong place, then it will break the code here, right? Because we've done 3 minus, and then we put the comment operator, so it's going to ignore everything after that. So it's looking for a number to subtract from 3. Okay, and then a little comment about spacing, that R doesn't really care with the numeric operations. So here 3 minus 1 is the same as 3 space minus space 1. But when we're using sort of character strings, then it's going to obey the spacing. It's going to keep how many spaces that you've typed in. Okay, so R evaluates code line by line. So by that I mean every time we put an enter, then it's going to work out sort of evaluate that line and then go to wait for the next command. So it's not going to sort of run all the lines of code simultaneously. So occasionally you see this written in some people's code that they use a semicolon, and this is telling R to sort of take a pause, equivalent to like entering on a new line, and evaluate the command. So you can see here we've got sort of two commands, 3 - 1 and 5 × 9, and there's a space here. It can't really evaluate both of them at the same time, but if you put the semicolon between, then it evaluates 3 - 1, and then it evaluates 5 × 9. So I would say it's less common now to see this in people's code, but you might see it in some older R code that people are using semicolons to separate different functions. Okay, so this is where I would stop for the first exercise, and I really encourage you to sort of go through these. So here we can sort of see them on the screen, but yeah, the idea would be that you go to the exercise folder in the handout, and then you open up exercise 1, and then you can follow the commands. So here I've put in the comment, right, the sort of question, and then you can type your answer up here, and then we can press the run, and it will run it for us, okay? And then we can do the next one, 2 ÷ 8. And again, I can press Control Enter, remember, to send it down. Okay, so I would really, yeah, maybe I just point out as well that the solutions are here as well for exercise 1.1. So they're all sort of completed here. But I really encourage you to work without the solutions and to go through each of the questions and try your best. Like I say, R is like a language, right? So the best way that you can learn it is practice. And so it's really important to commit the time to practicing. Okay. So like I say, in the classroom, I probably give the students maybe probably 30-40 minutes to do this, or maybe a bit less, maybe about 20-30 minutes to do this exercise at least. Okay, so a little bit about functions. So yeah, R comes with many pre-installed packages that contain the functions. I should probably be saying here. So installed as part of the base package. It's located in the library directory. So the functions have names. So every function has a different name, and they all take arguments within the parentheses, right? So by that I mean this is sort of a very general form of an R function, right? That we have the function name, and then we have these different arguments, like we've met before, where we talked about the mean function, and then it had an argument called x, and then a second argument called na.remove, right? .rm. So the arguments you can think of are like options or inputs for a function, and each function has different arguments, and we separate these different options, these different arguments, using commas. So I think in Stata we use spaces, but in R we use commas to separate the different arguments. And just like we talked about before, we can find out these different arguments using the help file. So we can look up the help file using the !log. You might have noticed as well that RStudio has this sort of auto completion that's very nice. It can help you stop making so many typos, which I used to do a lot. But you can sort of use these auto completions along with the tab button on your computer to help you complete the typing of the function names. Yeah, so maybe let's do that in RStudio so it's clear. Okay, let's make this bigger. Maybe let's do it in a script. Right? Okay, let's delete this. Okay, so when I'm typing log, you see RStudio. Okay, we see RStudio pops up this screen for us. Okay, and if it doesn't pop up, you can press the tab. Okay, it pops up there when we're typing it, and we can already see a part of the help file appear, right? And also lots of different possible functions that you are looking for. Okay, So say we choose the log 10, yeah, then we open the parentheses, and now I'm going to press tab. And so when I press tab, it opens up the two, or what do we call them, arguments, kind of options that are available to us, right? So here we've got X and base, and then in the yellow here is like kind of the section in the help file to describe each of these arguments, okay? So say I press tab again, and then it's already written for me X equals, right? I didn't have to type this. I mean, in this case, writing X is not complicated, but sometimes the argument names can be easy to make a typo one. So I can put the number 10, for example, is what I want to log. And I can press comma, and then I can press tab again to get the base. So now I can press clicking on it this time and say I want log to the base 2, for example. Okay, sorry. Let's undo that. Okay, and then I can run this line of code. Let's just do it like this, press run, and then we can get the result here. Okay, so this tab key is very, very useful, and it's only sort of not available in the sort of basic version of R, right? In RStudio, it's where you can use it. And so this allows you to sort of really write code quite quickly, right? Because usually if you keep on pressing tab, then you can sort of use the up and down buttons to select which argument names you want to be kind of auto completed for you, and then you can just type in the inputs that you're worried about. Okay, so we can see a bit more detail about the log, right? We can enter in a value that we want to take the log for as X as the first argument, and the second argument is the base. So by default, the base is equal to the E, right? The exponential of 1. But we can change this default if we want by putting in a different number here. So log 10 to the base 10 is 1, whereas log 10 to the base E is 2.3, or the natural logarithm, as we tend to say. So R knows what arguments is applied to the function and the order, right? So we don't have to write log X is equal to 10. We could just write log 10 and we're going to get the same value, right? We don't have to write the argument name, the option name. But it's a kind of good habit to always do this, because you can forget what the order of the arguments are, or what they are. So having the name there can help you look it up. This is sort of a second example, right? Here we put log 10, 10. So this is the same as doing log X is equal to 10 and then base is equal to 10. It knows that the first one is the number you want to log, and the second one is the base that you're going to use. But yeah, so these will both work, both be accepted. And yeah, this is just me advising again that it's better to write out these names, because it's a bit easier, especially when you look back at that code, or so if you give your code to someone else. And remember, when we use the tab in RStudio and enter, we can sort of get away without writing it, right? It's kind of auto-completed for us, so it's not too difficult to write them out. Okay, so here is just a little table of basic sort of mathematical functions available in R when you load R, so without requiring any extra packages. And in this exercise, we're sort of practicing these functions. So going back through them, maybe looking at the help file and checking that we have the right argument names, and completing these exercises. So again, with this exercise, I'd probably give about 20-30 minutes for the students to complete them. So I really encourage you to work your way through it when you have the time. Okay, the next part that we talk about is on logic. So logic operations are essentially when you can give a statement to R and it will try and evaluate it as true or false. So this will be the output rather than a number or a bit of text string. So this can be really useful when you're doing data manipulations. Perhaps you want to filter data according to some true or false statement, for example. Okay, so these are sort of the basic logic operators that exist in R. So we have the less than or less than equal, greater or greater than equal. To see if someone is equal, we use two equal signs. And if it's not equal, we use the, how we would say this, exclamation mark and then the equals. And finally, these two are a little bit more complicated. This is for when we want to find matches to multiple logical statements, right? Where we use the and or the or, the bar for the or. So to give you some examples, so pi, right? It's a special number and it's already stored in R. So when we type pi, we see it just prints it out to 6 decimal places, but in fact it's stored to many decimal places. So we can do a test on pi. For example, is it greater than 5? And we get false. This is just an example of the and or. So we can say is pi greater than 3 and is pi greater than 4? So this is false, right? Because at least one of these is false. And this one we're looking for is pi greater than 5 or is pi less than 4. So this is true, right? Because at least one of these is true, right? So pi is greater than 5, less than 4, for example. So again, this is where we would pause the video, pause the class, and spend some time practicing with logical operators. So you can sort of try and work your way through these exercises. Okay. So next part to talk about is assignments and referencing. So far, a lot of the times we've been typing into R directly, right? And that we've been just doing some basic operations. But like I sort of briefly mentioned in the last set of slides, we can sort of assign or recall operations that we've done using this assignment operator, which is the arrow, right? So this is like a less than and then a dash next to it, right? So this will allow us to save our objects or create our objects that save the manipulation after the assignment on the right-hand side of the arrow. So see, when we've typed in this bit of code, like A is assigned the value 1 plus 2, we don't actually see the result, but the result is stored in a little bit of an object, a little bit of memory stored in the computer. So if we type A again into at the prompt, then we can get the answer out. And what is happening, it's not like recalculating, it's just does the calculation once and stores the result, and then we can see the result printed for us in RStudio. Let's do this up here, right? A is equal to, let's say 10 times by 4. Okay, so I run that code, and then you can see it's created here, A, and we can already see the result in the how would we call it, the environment tab. And then when I type A down here as well, we can see the result printed to R for us to view. Okay, so a few rules or cautions about creating objects like this. We're using the assignment. So we can't create a number, right? So we can't call anything, we can't save it, overwrite a number and call it, define it like this, okay? And we also can't use a number to start the definition of any object. So in this case, we've tried to create an object called 3a, but we will get an error message. We could call an object though a3, and we wouldn't have any problem so long as we don't start with a number. Okay, the other point to mention is that we can actually create objects called taking the names of functions that already exist, right? So we could write exp is equal to 1 plus 3. So before doing that, we can write exp and it tells us that it's a function in R. And then we can override it and saying exp is equal to 1 plus 3. And then when we type exp, it says it's 4. It's no longer a function, right? It's 4. So what is happening is we're sort of creating different layers on the different layers of R. Remember, we've got those packages in the global environment. At the top layer, we've created an exp. And further down, there's an exp in the base package. Yeah? So this exp function will still work. We can still exponentiate a number, but it's lower down in the search environment. So we won't recall it directly when we type it into R. So it's a kind of a little bit dangerous in R to be creating your own objects. Well, it's something to be aware of, that this might break your code later on if you're creating objects with names of functions that already exist. So it's always good practice to type the name of what the object that you want to create, just to check that it's not going to print out something like this. So if it's saying it's a function that it already exists, then choose another name to create for the object. Okay. This last point is just saying we can sort of still directly call any function from any package by using this format, where we put the package name and then 2 colons and then the name of the function, and it will allow us to get to the exp function. So you don't truly like delete it; it still exists. We can still get to it, but it makes things a bit more difficult. Okay, so another point is that R is case sensitive, right? So when we do capital A, we don't get what we might be expecting if we from creating this object 1 plus 2, right? That was A, 3. So you need to be careful with your upper and lower case and you're using the right one. And this is just repeating the point, right? If you're not sure if a potential object has a name itself, is already sort of being used in R, then just type the name that you want to call it, and then it will tell you if there's that object exists or not. So here it's saying object E is not found, right? So that means we wouldn't run into a problem by creating an object called E, just like we created an object called A here before. Okay. So named objects in R behave just like the ones that R already knows. So this can be very useful for building up more complex operations. So here we had A, and we can multiply A by 2, and then we get the answer 6, right? So it knows what's stored in A as a substitute for the number 3. And we can sort of create layers, right? So here we're going to use A, multiply by the square root of A, and save it as B. And then we get a B. So you can imagine this could be different steps in an analysis. Okay, so to see which objects we have created in R, we can use the ls function. So here it's just printing out the functions. But frankly, yeah, with RStudio, we can also see it on the right-hand side or in the top right in that Object Explorer. If we want to remove objects, we can use the rm function. So here we just want to remove B and exp, for example, and then we're left with A when we print it out. So this is going to be deleting everything sort of permanently. So you can either rerun the code to do that. And if you want to get rid of everything, you can use remove list is equal to ls, or the other option is this brush, this kind of broom here, right? So if I press this, it comes up, are you sure you want to remove all the objects? I say yes, and then everything's gone, right? So now when I press A, it's saying A is not found because I've deleted all the objects. Okay, so that's about creating sort of simple objects. And so far, we've only talked about objects that are of length 1. So that by that, we mean it's just like a single value going into A. But in R, we can sort of build a lot more sort of complicated data structures, let's say. So one way to do that is to build a vector, right? So this is like a set of numbers of a common format. Or yeah. So the most basic way to do that is to use this C function. So this means to concatenate, right? To join together different elements. And we separate each element of the vector using commas again. And so C is really important in R, right? Because so make sure you don't create an object called C like we just created an object called A and B. So here we're going to use C to store together the numbers 1 to 10, and we're going to store it in an object called V1. So you can see it's printed out here. And here we're going to create a second vector, V2, which is going to be the letters A to D. Yeah. We print it out. Okay, if we are creating a vector that's a combination of numbers and how we say text, then it will automatically convert everything to text. So it is not able to manage these different combinations or different types of elements going into the vector. So it's by default, it's gonna, if one bit is text, then at least one bit is text, then it will convert everything to text. So we can tell that, right, because it's got the quotation marks and it's in green. Okay, up here it's in blue. Okay, so once you've got a vector, you can combine it with other vectors. So in this case, I've combined V1 with V2 and then V1 again, right? So I've got 1 to 10, and then we've got A to D, and then 1 to 10. Remember, originally, right, V1 was numbers, but because V2 is letters, it's converting everything to letters again. text again, sorry. Okay, so you can hopefully realize it can be quite tiresome to type out everything that you want in the vector, and so there's lots of useful functions to help create vectors in R. So rather than manually typing, so one is the colon, and this effectively tells you sort of tell R the first and the last number, and then it fills in the rest of the numbers for you. So 1:20 means you want the vector 1 to 20, and you could go backwards as well, right? So you could go from 10 to -5, and then it's going to print out the whole numbers between them. If you want something more complicated with sort of more like not in steps of 1, for example, we can use the sequence function. So the sequence function has an input from and to, and then it also has another one called by. So if we use from and to and go from 0 to 10, then we get the same as before that we had for that object A, because the default is that it's going to go by like in steps of 1. But if we put by 2, then it goes in steps of 2, right? So you can see you can get a slightly more sort of complex vectors being built from that. Okay, it also has a length out option, which allows you to specify the length of the vector, right? So here we're saying we want a vector, a set of 25 numbers to go between 0 and 10, and then it will work out that each step has to be 0.416. Yeah, so every 0.416 it's creating the new element in the vector that has to be 25 by definition. Yeah. Okay, so that was the sequence SEQ function. There's also a REP function, which allows you to sort of build repetitions of repeated elements within a vector. So here we're going to repeat the number 0 10 times, or we can repeat the text hello 3 times, or we can repeat the vector v1, which we've already defined as 1 to 10, and we're going to repeat it twice. And it's also got an each argument. So rather than repeating like each time, we can repeat each element multiple times. So here we repeated the vector, which remember was A, B, C, D, and we're going to repeat each element twice. So in this case, the order of the repetition sort of changes a little bit when we use each. Okay. So a little sort of important note is that vectors is sort of very much key to R. That R, many functions in R sort of built to work with vectors, and so that is essentially right these sort of columns of numbers. And so a lot of operations that we do just with single values in R, they work with vectors as well. So for example, if we wanted to add v1 to itself, then we can do that. Or if we want to square every element of v1, we can do that. Or if we want to log every element of v1, then we can do that. And usually, this is where the way R is sort of built is to handle whole columns of data. So usually functions are kind of designed to take vectors and to work really quickly with them. Okay, so again, another exercise for you to take 20-30 minutes to try and practice creating vectors and saving them, and using the SEQ function, using the REP function as well. Okay. So some other functions that sort of less still sort of mathematical, but sort of are in the base package that are sort of especially useful when you're working with vectors are listed here. So if you want to sum to get the sum of everything within the vector, or the minimum, for example. If you want to sort the vector or reverse the vector, if you want to find how long the vector is, if you want to build a table of the vector, then you've got all these sort of different functions that come in the base package. Okay, so this last one we'll just talk about. This can be very if else can be very useful when you're working with data, and perhaps you want to create like a categorical variable. So imagine we have we want to sort of create an action based on a statement true or false. So in if else, there's 3 inputs that we can give it. So one is the test. So this is a statement that we need to say. The second is what happens if the test is true, and the third is what happens if the test is false. So imagine we got this v1 vector, and we want to test whether v1 is greater than 5. So here we can run this as before. We can see the first 5 are false, and then the second 5 are true. And then we can put that sort of statement or similar statement inside of if else. So here we're going to use v1 is greater than 8, and we're going to say we want to return the bit of text high if v1 is greater than 8. So for the 9th and 10th part, and no if it's less than 8, or if this is not true, right? If v1 is not greater than 8. So if else allows us to sort of create these categories, and we can either do it returning text, or we can do it returning numbers. In this case, we used 1 and 0 rather than these text low or high. So again, another exercise to practice, to go through. Again, I'll probably give a little bit longer for this one, maybe 30-40 minutes to get familiar with these different functions. It's based on this sort of table, and getting familiar with how these work. So these are sort of quite good to have a good basic knowledge of each of these functions, especially when you come to working with data frames and I'm wanting to make some summaries of them. Okay, so the next sort of part is talking about statistical functions for vectors. So in the stats package, which is one of the 7 that are loaded by default with R, it's these sort of basic statistical functions to calculate the mean or the median, the standard deviation, the correlation, interquartile range, or the summary. For example, there's actually many more functions, but maybe these are some of the most common ones. And we can also sort of use R to generate random numbers, so different types of random numbers. So sort of the most basic sort of random generation number is the sample function. And this will allow us to draw samples randomly given a vector. So we give the vector v1 to sample, and we say we want a sample of size 5. And so it's going to randomly sample 5 different numbers for us. Of course, if you do this on your computer, you'll probably get a different set of 5 numbers out, right? It's all sort of randomly done based on a seed on your computer. And here in the second example of sample, again, we're going to sample from v1, and we're going to take a size this time of 15. So we want 15 numbers out, and we can set replace is equal to true. So this means we can draw the same number twice if it occurs randomly. So after sample, we also have well, here I just give an example of 4 different random generating functions from the different sort of distributions, from a normal distribution, binomial, Poisson, and a uniform distribution. There's actually like probably, I don't know, maybe 20 or 30 functions like this from different distributions in R, and they all start like R, and then the sort of an abbreviation for the distribution that you want to generate from. And they all sort of work in the same way, that the n, so this is the size of the sample that you want, is the first argument, and then the second or third, or depending on the distribution and the number of parameters in the distribution come later. So for the normal distribution, right, we have a mean and a standard deviation, whereas a binomial distribution, we have a size and a probability. And again, it just draws the numbers randomly from that distribution. It's Poisson and the uniform. Okay, so again, this is practice with using sort of these random sampling, how should I say, statistical functions in R. So again, I'll probably allow yourself 30 or 40 minutes to try and complete this exercise before you take a look at the solutions. Okay, so a little word about objects. So R is a object-oriented language. So maybe we sort of hinted at that before, but like everything in R is an object. So everything that we do, everything that it creates, everything that we manipulate is an object in R. And objects are really like a good way to think about them. It's like a little bit of memory, like you might have had a memory button on your calculator, but we have sort of a lot more freedom with objects. And objects come in many different types and flavors, right? So far we've sort of met this already, right? Pi, right? So this is like an example of a one-dimensional object, right? So it's an example of a vector, and in a vector sort of can be of different lengths, right? So like pi is of length one. The object letters, which is also like contained in R, in when you load R. This is again a vector object of length 26. Yeah, it has 26 different elements to it, and so you can see, okay, in pi there's only one element of it, but it's a numeric. It's a numeric type of vector. In letters, it's slightly different, right? These are all in green because they're character strings, they're bits of text, and so they're all of the same type. And this is the key to vectors, that we'll always have the same type of elements in the object. So after vectors, so remember, vectors is just like a single column is the best way to think about it. So you can get a matrix, which is like a two-dimensional object, right? Where we can have, again, all elements are of the same type. So here they're all numbers within there, but we have 2 dimensions, right? We have the row and the column, whereas before with the vector, we just had sort of a set of numbers. So we can build matrices using the matrix function, and then we can say here we're just filling the matrix with the numbers 1 to 12, and we're saying how many rows there are. We can say how many columns there are, and then there are other options for matrix. So far, right, we're talking about objects. We've got vectors, which are one-dimensional, matrices that are 2-dimensionals, and we've got data frames. Again, data frames are sort of 2-dimensionals of a type of objects, but they're a bit different from matrices. They essentially you can fill a matrix or a data frame with columns that might vary by type. So in this case, right, we've got some numbers in each column, but it might be that we could fill one of these columns with some text, right, a label, a category, if we wanted to. Okay, and again, we have row and columns, and this is a data frame called Swiss, which is loaded when we load R in the datasets package, which is one of the 7 that we load up with R. Okay. So we've talked about vectors, we talked about matrices, then data frames, and the third type of objects. I mean, there's many different types of objects, but perhaps the fourth type of object that is important to know about is lists. So lists are like vectors, but they don't have to contain elements that are all of the same mode. So not everything in the list has to be all numbers or all character strings or all logical, right? So here we've built a list, and it's contained different elements containing different parts of different types, different modes of data. So in the first part of the first element of the list is a kind of vector. So it's an object, a different mode within the list. And the second part, we've got these numbers 1 to 10, and the third part, we've got a matrix. So lists are super flexible. They can contain many different types of modes. Whereas remember, like a vector or a matrix, we have to have the same mode of data for all the elements. Okay, so lists are used a lot in R. So for example, a regression result in R, what's usually returned is a quite complicated list. So here I've just run a regression model using the LM function, which I'm not going to talk about too much in this course, but here we sort of give the regression model that we're interested in and the data set, which is the Swiss data set that we had before. And then we can save the object. And here I saved it as an M for model. And we can look at the structure of the model, of what's saved. And you can see there's lots of information in here. And it's got, it's basically, well, it's a list, essentially, right? And we've got 12 different elements to the list. And here we're only seeing on the slide what the first 7 or 8 of them. And even within some of the elements, there are some more complicated parts to it. Okay, so I talked about this a little bit already, right? That all objects have certain modes or modes that they can deal with. So some objects can only deal with one mode at a time, like a vector or a matrix, and others can store multiple can store elements in multiple modes, like a data frame or a list. And so some of the basic modes that we usually come across are integers, like we were dealing with that vector A, which was the numbers 1 to 10. Numeric, which is sort of anything on the real number line between minus infinity and plus infinity. A character string, which is sort of text, as we talked about before, and logical, that's when they're containing true or falses. Okay, so that's mode. So the next little section is on indexing. So yeah, sometimes, well, indexing is useful for when we want to select subsets of a particular object. Yeah. So sometimes we might not want to print, or we might want to manipulate, or we might not want to plot like an entire vector or an entire matrix or an entire data frame. So indexing allows us to select different parts of an R object, or even to select and adjust values in our object. And it's done based on these position integers. This means we can say we want to take the second part, or the fourth part, or the eighth part, for example. And we select these positions, select different parts of a vector using these square brackets. This tells us that we're looking for a subset of the R object. So we put the square brackets after the object to say that we want a different part of it. So here I've created a vector v4, which is just 1, 2, 3, 4, 5 different bits of text. And here I'm saying I want the third part of the vector v4, which is this part like. Okay. And this second part we can use this second sort of input. I'm saying I want the second, third, and fourth part, right? I want from 2 to 4. So this is really like chocolate, right? So it's getting the second to the fourth part. And here we can use a different part, different combination. Here I'm saying I want the first, the third, and the fourth part. Okay, so I'm using the square brackets again to say I want to select a subset, and here I'm giving the integer, like the value, the position of the parts that I want to extract from it. Okay, we can also use the minus with this. So this is saying I want to take v4 and I want to drop the second part by putting -2. So then we just get a vector out that's only got four characters in it, 4 character strings in it rather than 5. And we can also replace parts of it, right? So say I want to take the fourth part by doing square brackets 4, and then replace whatever the fourth part is with the word with the text strawberry. Yeah. So then this changes v4. So we can use the indexing in combination with the assignment. Okay, so indexing also works with matrices. So so here we define a matrix, which is just a simple 3x4 matrix, and then we can use the square brackets to select a part of this matrix. Yeah. So say we want to take the third row and the fourth column, then this is the element 12, right? That is taking the third row and the fourth column. So yeah, it works in this format, right? That we get the square brackets, then the first number is the row and the position on the row, and the second number is the position on the column. Okay. In this last example here, if we leave like the row part empty, then it's assuming that we want all elements from that row. And here we can put the column number. So here we just say we want the third column essentially, which is 7, 8, 9. So we can print out the third column here and take all rows. So this sort of format also works with data frames. So we can again use the square brackets with a data frame. So here with the Swiss data frame, for example, I'm taking the 38th row and the first column to give me the value there. Okay, so with data frames, we also have some additional flexibility that we can use the names of the data frames. So if the data frames have row labels and column labels, then rather than put the number, like the 38th row in the first column, we can say the row, the value in the row named Sion, and the column in the column named fertility. So this is the same value we're looking up here. And also with the data frame, we can also use this dollar notation. This dollar notation is telling us to select the entire column. So we have the format that we use, the data frame name and then the column name. So here we're going to take the Swiss data frame, and maybe it's easier to look at this last one. We take the Swiss data frame and then the whole of the fertility column, and it prints out the whole of the vector for us. If we wanted to like the 38th part of that vector, then we can do the same, but just put square brackets 38. Yeah. So this dollar indexing also works for lists. So in this case, remember we created this regression model M. And if we want the coefficients, then we can do M dollar coefficients because it's stored in M under this name coefficients. And with lists, we can also use square brackets, but we have to use 2 square brackets to get a subset of a list rather than one. So this gives the same result. It's the same way to look up the coefficient element of a list, of a model list. Okay, so that was talking about indexing, and then this part we'll talk about missing values. So of course, missing values make up a large part of statistics. So R has very good capabilities for missing values, and the most important thing to remember is that NA is used in R to represent missing values. Yeah? So when we type NA, at least in RStudio, it's going to show in a slightly different color. And this allows us to sort of say that we have a missing value. And when you read in data as well, you might get NAs where sort of cells might be missing. So here we're creating a vector V5 that takes the number 10, 7, then 2 missing values, then 0, missing value minus 2, and 8. Okay, so the important thing to remember with missing values, when they're present, it might mean that the results from your functions might not turn out as expected. So in this bit of code, I'm asking for the maximum of V5, this vector that I just created, and I get an NA out. And that's because it doesn't know what the maximum is because of these missing values. So this value, right, could be 11 or it could be 0, right? So it's not willing to evaluate it for you. So it's just saying it's kind of unknown what the missing value is. So lots of functions in R have this argument name na.rm. So this is, do you want to remove the NAs? Do you want to remove the missing value? So if we set that to true, then we get a different value out. So we get the rather than getting an NA out, we get the how would we say, the maximum of the existing values. So we can test for whether there's missing values as well. Perhaps we want to filter a data frame to look at where the columns are using the isNA. And this is going to say whether it's true or false, if the value is missing or not. And then the opposite is using the exclamation mark in front of isNA. So this is the reverse, right? This is testing for non-missing values. And some functions work normally. They can handle NAs, so you don't need to write NA remove. So summary V5 sort of works as normal, but we get an additional column with telling us how many NAs there are in the data. So again, this is another exercise just to practice getting used to indexing and working a bit with missing values. So I would probably allow yourself maybe 30 to 40 minutes to go through these 8 questions and get used to it. Okay, maybe I'm a bit aware of time, but maybe I can push on to finish off these slides rather than take a break. I think maybe it would be more sensible to keep it together. Yeah, okay. Well, I continue just to finish off. So the last main part of these slides is to do with functions. So this is sort of a bit more advanced level R, but I think I just like to put it in the course just to make you aware of this sort of capability in R, rather than giving you sort of a complete course on functional programming, but just to give you a kind of overview. So by programming language, we sort of mean that we can create our own programs, our own functions. And to do this in R, we use a function called function. So it's kind of a little bit complicated to get your head around. But essentially, when we want to create a function, we need to use the assignment and then the function. And we use functions to sort of wrap up code that do repetitive tasks and sort of simplify complex tasks. And yeah, when we create a function, the idea is that we sort of want to give a sort of friendly access to the R code. So functions can take this general form where we have the function name, then our argument names, and this means, and then we have a set of actions. So this might be just one line of code, or it might be 50 lines of code. And then at the end of after the actions, we will return a value. Okay, so we can wrap many different types of actions inside the function, and we can specify as many arguments as we like. And we can set these arguments to either default values, or we can set them to null, which means we don't have a default value, that when we come to use the function, we have to force the user to set a value. The return part at the end here is not strictly sort of necessary. So what will happen is if you don't use it, that the actions will take place, but nothing is outputted unless we print the objects in the last line of the function. Maybe it's easier to see with an example. So here I've created a function, yeah, and I've done that using the function called function. So on the left-hand side of the assignment is the name that I've created. So I've called it my square. I've used the assignment, and then I'm saying I want to create a function. So I use the function here, and then this function is only going to have one input, one argument, and this argument is going to be called x. And it's going to have a null input by default, which means it doesn't know what x is by default, right? And what's going to happen within that function is whatever the value of x is, it's going to be squared, and then I'm going to save it as y, and then I'm going to return the value y once it's been created, once it's run that line of code. Okay. So once I run this bit of code creating the function, I can use it, right? So here I use my square, and I say x is equal to 2, and then that's the same as writing 2 to the power of 2 and printing it. And here I can change it to 10. Okay. So this second function is sort of based off this first function, but it's a bit more complicated. So again, rather than call it my square, I call it my power. I use the assignment, and I say I want to create a function. So I'm using the function to create a function. And then I'm going to say x is equal to null again, but I'm going to have a second argument called p. And then by default, p is equal to 2. And whatever p is, I'm going to use it to raise to the power whatever x is. So I can put in any number for x and any number for p, and it will return the value, calculate the value and return it as y. So here I do my power, and I put x is equal to 2 again. And because by default, p is equal to 2, it's the same as doing 2 squared. Okay, but in the second use of the my power function that I just created, I'm going to put x is equal to 2, but I'm going to change p from its default value of 2 to 4. So this is the same as doing 2 to the power of 4, right? So this gives us the value 16. So this is a sort of a very simple illustration, but hopefully you get the idea that functions, we define it using the function, and then we can define how many inputs we like, however many we like, and then we can have some actions that could be one line here, or it could be multiple lines, and at the end we put a return to give an output. Okay, so the second part of programming that I wanted to cover was for loops. So these are used for carrying out repetitive tasks, and so they sort of take this general structure where you write for, and then we have this sort of statement. Maybe it's easier to show in the example. You sort of have an element which is going to be updated, and then a vector for the set of routines that you're going to carry out, and then we use these curly brackets. And inside the curly brackets, we put the actions that we want to repeat within the for loop. So maybe it's easier to skip through this and show you the example. Okay. So here I'm coding a vector V8 that's going to be missing to start off with, right? So this is just 12 empty, a vector of length 12 with all empty, okay? And then I'm going to write a for loop. So I'm going to write for to say I want to do a repetitive task. Then I use the normal brackets, and inside I'm going to say I want to use I as like a temporary kind of part of the code. and I is going to take different values between 1 and 10. Yeah. So this is where I use you write I, which is kind of chosen by me. In is what is required in the for loop, and 1 to 10 again is chosen by me, that I want to do this task 10 times. Yeah. And then inside the curly brackets is my repetitive action. So in each time, I'm going to change the value of I. First, it's going to be 1, then it's going to be 2, 3, 4, and so on up to 10. And for each value of I, I'm going to put it into this function rPoisson. So rPois is generating a random number from a Poisson distribution, and it's just generating one number here. And the mean of that function, first off, when I is 1, the mean is 1. When I is 2, the mean is 2, and so on, up to 10. Once I've created this random number, x, I'm going to create a message, which essentially is going to print it. So it's going to print the number, and then I'm going to store it in V8. So in the first part, when I is 1, I'm going to store the random number generating from a Poisson distribution with mean 1. And say, for example, in the fifth part of the loop, then I'm going to generate for the fifth element, the random Poisson, the number from a Poisson distribution with a mean 5. So you can see, if the way to maybe imagine this is you start out with a value 1, and then you run this 3 lines of code. So you say lambda I is 1, so I generate a random number with a mean 1 from Poisson distribution. I print it, and then I save it as the first part. Then I is 2, and again generate a random number, print it, and then save it in the second part. And then I is 3, and again go through the steps until I is 10. So once we run this function, you can see this is what is being printed out. This is the message part here. The first when I is 1, the mean value generated was 4. When I is 2, the mean value generated is 0. When I is 3, the mean value generated is 4, and so on up to 10. And then this V8 part is because we updated V8. Before it was all NAs, and now in the first part, we saved the value 4. In the second part, we saved the value 0. In the third part, we save the value 4. And you see V8, remember, it was of length 12. So the first 10 numbers are being filled up going through this for loop, but the 11th and 12th haven't. And that's because we ran the for loop only between 1 and 10. And so when it comes to 11 and 12, we stopped the loop before 11 and 12. So it didn't get to generate an 11th and 12th number. Okay, so for loops can be really useful for doing very repetitive tasks. For example, we might want to imagine that you had an Excel file with lots of different sheets, and we could sort of use this read Excel. We'll talk about the read Excel function more later, but we could read in like sheet 1, sheet 2, sheet 3, up to sheet 10, read it in, save the data as D, then use that data frame D in a regression model, for example, and then write a CSV file to save the coefficients, right, depending on the model. I will get into more detail about write CSV as well later on. And hopefully you can get the idea that now we can sort of program very sort of complicated tasks like this, like reading in different data sets, running a regression model, and saving the results using a for loop. Rather than writing out the code like 10 times, we can write it out once and then use a for loop to wrap it up. Okay, and here's another example of a for loop using a basic population projection. So imagine this is a very simple population projection model where the population next year in time t+1 is the population this year multiplied by 1 times the population growth rate. So imagine we can do this in R using creating a vector P, which is just going to be, say we're going to want to create a projection for 10 periods. And the first period, the baseline population is going to be 100. And then we can go do a for loop where for the next 9 periods, we can calculate what the projected population is going to be by taking whatever the value, the current value of the population, and multiplying it by 1 times by the growth rate, which here I set to 0.05. So imagine I is 1 to start off with, right? Because we start the loop at 1. So P1 times by 1 times by 0.05. So P1 is 100. That's going to create our P2. And the second part of the loop, I changes from 1 to 2. So if P2 is going to be whatever we just created in the previous loop, which is what 105 times by 1.05. And that creates P3, and so on up to P9 will create P10. So when we print P at the end, we see the projected population of this very simple population that started at 100 and grew at this rate of 0.05. So we can sort of wrap for loops within a function, right? So we can take the initial population here. So I'm creating a function called SP rate. I'm creating a function using the function, and then I put P0 is equal to null, the rate is equal to null, and N is equal to null. So P0 is the initial population, R is going to be the population growth rate, and N is going to be the number of steps ahead that will project the population. And then I can create this very general function. It's going to take whatever the initial population is and multiply it by the growth rate and run this for however long we want, depending on the N, and return the sequence of projected populations. So here I've just done it with, like before, with only for 5 periods using the same growth rate, starting at 100. Here I've done it for a separate population growth rate 0.1, a separate starting population 20, and for 20 periods as well. So you can see in R, it's a little bit complicated, but once you get familiar with how to write functions, you can quite quickly create some quite powerful functions to sort of do quite complicated bit of analysis. So exercise 8 is practicing writing some basic functions. And again, I'll probably allow 40-50 minutes perhaps to go through this exercise. And in this exercise, and sometimes else in the rest of the course, I use these 5 comment sections here. This is sort of, I give you a template of the code, and the idea of these exercises is just to replace whenever I've got these 5 comment signs to sort of change the numbers according to the questions. So here we want to create a function with inputs ASFR. So you would delete the 5 here and write ASFR. Okay, so just a little bit towards the end. So R, so it's a bit separate from what we talked about, but it's the idea of setting up R so that you can import data or save data or a plot. And that R sort of works in a particular location on your computer, right? When you load up R, usually if you're using Windows, it will be in like My Documents, yeah? And you can find out where you are on your computer using this getWD. And usually, unless all your data is in like My Documents, for example, then you want to be able to change your location to make it easier to read in data, to run scripts, and to save the data and plots and other inputs, outputs that you might have in the correct place on R. So the easiest way to do this is to use RStudio and to use a project folder, an RStudio project folder. And so this allows you to sort of tell your R session to work in a particular directory on your computer. So to create a project project file, you can do a file and then new project, and then you'll get this kind of wizard. And you can either create a new directory on your computer, or if you already have a directory where your data is, perhaps you want to use an existing directory. And then you can, it will create an R project folder. Maybe it's better to show you an RStudio. Do you mind to mute them? So, okay, great. So going back to this. So when we do a file and then new project, we open up this folder. Okay, I don't need to save this. Where will we file? New. Oh, okay, it was just taking time. So then we can choose an existing directory. And so then we can browse to where we want, and then you create a project. So I won't do it here because it's already created. So what this does is create this kind of icon here, right? This little file, right? It's only 1 gigabyte. And it has this little blue symbol. And this essentially is telling you, giving you a link to that directory to work with in R. So if I double click this, then it's going to open up RStudio, and it's going to make sure that I'm in that location on my computer to read in or save files, right? So I can go to a different one for you. For example, let me go to like a project that I'm working on now. So here I have the R project file, and then I'm going to double click this, and it's going to open me up in this the same location, which is in my E drive, right? Which is in this project folder that I'm working on. So I can see it's a slightly different setup, right? Where I've got different data and different functions in there. So this was the handout for the one that we have already. Okay. So you can check this location using getwd. Yeah. So then we see the where you are in your computer. You can also see it's written here at the top of the console, and also using the sort of default sort of setting in the file environment. Okay, I think I put that in the slides. Yeah, okay, so this is what I'm talking about here. And I'll just skip back, okay, to here. So once we've created these project folders, then we can load data or save plots using this the sort of path that we want to use on the computer, on the location that we're doing. So we'll talk about read CSV later, but for now, it's just important to remember when you read a file in R. So say we've got this file that's called survey.csv, and it's in this folder. Then we can give the whole of the address for that file, and there are certain sort of things that work and things that don't work in R. So if we use the /1// then this will work, or we can use 2 backward slashes, and this will also work. But when we use 1 backward slash, so here we use 2 everywhere except right at the end we only used 1, and then it got confused. So if you just use 1 backward slashes, then R will have trouble reading in data or saving data to a location when you use one backward slash. So it's good to always use 2 backward slashes or 1 forward slash. Okay. Another important thing to remember when working with like the locations of your data or plots is and R is to use the relative paths. So remember, like a forward slash here is sort of telling you to look within a folder afterwards, right, in the file system. If we do that slash, then that denotes you want to look in your current folder that you're working in, and then the subfolder after that, right? So we could say if we are in this folder, like teaching folder, and then we want to look in the data subfolder, and then the survey CSV is within there. We don't have to write out the whole address, right? C users guide teaching the data survey. We can just write dot, which is where we currently are in R, then look in the data folder, and then look for this file. Yeah? So this is what we call a relative path. And we can use 2 dots to work out, to go to a sort of a folder above where we are, and then a subfolder within that. So imagine I've got a folder, one called teaching and one called research. Yeah, and the CSV file I want is actually in the research folder. So in that case, I'm in this location teaching. I want to go up to the research folder and then into a data raw folder, and then then I want to read in this CSV. So the 2 dots are used to get like to something. Imagine it's a tree, right? So if you want to go down the tree, you just use a dot. If you want to go like across and then down, you use 2 dots. Okay, this was just talking about looking for the location that you are. And then, yeah, the final bit is sourcing. So with any R script that's saved.R, we can source all the code in that R script using the source function. And sourcing means like run everything inside that script. So it's the same as getting the whole script, highlighting everything, and pressing run. But rather than open up that file and go through that step, we can use the source function. So I use this later on in exercises. So that's just to basically explain what's going on with the source function. Okay, so sourcing functions can be useful, especially when you have like a complicated R project. that you will usually want to break your scripts, your R code, into multiple files, like one for reading the data, one for cleaning the data, one for plotting, doing plot one, plot two. You usually want separate scripts. So this is going to sort of really help you with your workflow, is using source to sort of just run the script in one line of code, and allows you to kind of give a sort of tidy working system to give you a nice workflow. And yeah, it also means you won't get too many objects in your sort of R environment, and you can quickly identify any errors that might be going on, or changes that need to be made, rather than having one long R script file. So it's always good to break it up. Okay, so I think I've overran there, but let's 70 slides, so tough to fit it all in the hour. But anyway, let's take a break for 10 minutes, right? And then we come back for the next set of slides.